Every single time you stream a movie, hop on a video call, or even just scroll through your phone, you are tapping into a massive, global network of invisible highways. But these highways aren't paved with asphalt. They're made of pure light. Today, we're going to pull back the curtain on the absolutely incredible world of optical transmission and find out how we actually send data at the speed of light.
So how do we get from a simple piece of glass to a network that spans the entire globe? Well, here's our roadmap for today. We're going to start with why we need all this speed in the first place. Then we'll get into the basics of how you even send information using light. After that, we'll dive into a real game-changing technology called coherent transmission, see how the physical optical highway gets built, and finally, look at how these networks are becoming incredibly smart.
Okay, first things first. Let's talk about the problem we're trying to solve. Our entire world runs on data. Think about it. Every video call, every file you save to the cloud, every smart thermostat in every home, it's all adding to this absolute avalanche of information. Our appetite for data is just growing at a mind-boggling rate, and that creates a huge challenge for the networks that have to carry it all.
Which brings us to the one fundamental question that engineers have been wrestling with for decades. With this constant, relentless demand for more and more data, how does the global internet not just collapse under the weight, how does it actually manage to keep getting faster?
The answer lies in the almost unbelievable capacity of these modern optical networks. To help you wrap your head around a number like 96 terabits per second, that is the equivalent of downloading every single movie and TV show on Netflix, the entire library, in less than 1 second. It's a staggering amount of data, and it's all flowing through a single strand of glass that's thinner than one of your hairs.
So, how in the world is that even possible? Let's dig into the fundamentals and see how we actually turn light into information.
It really all begins with this incredible material, optical fiber. It's basically a very, very pure strand of glass, thinner than a human hair, that acts as a perfect little tunnel or a waveguide for light. It's specially designed to trap light signals inside and guide them for thousands of kilometers with almost no loss. It's pretty amazing stuff. But just sending one single beam of light down one of these fibers would be like having an 8-lane superhighway all to yourself for just one bicycle. It's a colossal waste of space. To really unlock its potential, we need a brilliant technology called wavelength division multiplexing, or WDM for short.
This concept right here is the first major key to unlocking all that massive capacity. You know how a prism takes white light and splits it into a rainbow? Well, wavelength division multiplexing, or WDM, does the exact opposite. It takes dozens of different data streams, gives each one its own unique color, or wavelength of light, and then merges them all into a single super powerful beam to send down that one tiny fiber. And of course, at the other end, it splits them all back out again. Each color is its own private express lane on this light highway, carrying its own data totally separate from the others.
But just packing more and more lanes onto the highway was only part of the answer. To push data at speeds like 100 gigabits per second, and do it over really long distances, we needed a totally new way to encode and read the information that the light itself was carrying.
And that brings us to the real hero of this story, coherent detection. See, older systems were pretty simple. They could really only see one thing about the light, how bright it was, its amplitude. But coherent technology lets us encode and then decode information using multiple properties of light at the same time, not just its amplitude, but also its phase and even its polarization. It was a massive, massive leap forward.
Now, I know that sounds really complex, and the engineering behind it is genius, but the basic principle is just incredibly clever. So how does a coherent system manage to pack so much more information into a single beam of light? All right, I know this diagram looks a little intimidating, but the idea is brilliant, so stick with me. Let's just follow the light's journey. Over on the left, the transmitter is like a super sophisticated Morse code operator. It takes a pure laser beam and encodes data onto it, not just by blinking it on and off, but by precisely changing its brightness, its wave pattern, and its orientation. It's layering information onto the light. Then, after that light travels through the fiber, the receiver on the right catches it. And this is where the real magic happens. It uses a super powerful microchip called a digital signal processor, or DSP, that acts like a universal translator. It deciphers all those complex layers of information, and this is the incredible part. It can also digitally clean up any distortion or noise the signal picked up on its long trip. It's that digital processing that makes the whole thing possible.
So why was this coherent technology such a game changer? Well, it really boils down to a few huge benefits. First, you get a much cleaner signal that isn't bothered by noise.
Second, that powerful DSP chip we just talked about can digitally fix almost any damage that happens to the signal in the fiber. And what that means is we can send data at speeds of 100 gigs and way beyond over thousands of kilometers without needing a ton of expensive equipment in the middle. It is truly the core technology that enables the internet we have today.
Okay, so we've got the fiber itself, and we've got this incredible transmission technology. But how do you actually build a flexible living network out of all this? Let's take a look at the infrastructure that acts as the interchanges on our optical highway.
Believe it or not, it wasn't that long ago that directing traffic on these networks was a completely manual job. Seriously, if an operator needed to change a connection, a technician would literally have to drive to a data center, find the right rack, and physically unplug a fiber optic cable from one port and plug it into another. As you can guess, this was incredibly slow, easy to mess up, and a massive bottleneck.
Today, the solution is all optical switching. We use these intelligent devices called ROADMs. It stands for Reconfigurable Optical Add-Drop Multiplexers that are basically the traffic cops of the network. They can look at one single fiber coming in with dozens of different colors of light and then remotely redirect each individual color to a completely different destination fiber. And the best part? It all happens in the optical domain without ever converting the signal to electricity. It's all done in milliseconds, totally controlled by software. No more manual patching.
And what you're looking at here is the actual hardware that makes all of this work. These racks, these boxes, these are the physical engines of the internet. They are these incredibly dense platforms just packed with the lasers and the switches and the processors that power everything from a citywide network all the way up to those massive submarine cables that connect entire continents.
All right, on to our final section. We've got the speed, we've got the flexibility, but the next great frontier is making these huge optical networks truly intelligent.
To make that happen, companies are building a whole new layer of software intelligence on top of the hardware. You can think of it like an optical doctor. It's a system that is constantly monitoring the health of the light itself as it travels through the fiber, giving operators a complete, end-to-end digital map of the network's performance.
And this gives us some huge advantages. Now, the network can monitor its own performance automatically. It can analyze data to predict faults before they even happen. It can automate really complex jobs, and it can proactively fine-tune the paths that the light takes to make sure everything is running at absolute peak efficiency. It's a shift from just reacting to problems to proactively and intelligently managing the entire network. So, when you put it all together, here's the big takeaway. All of these different layers of technology, the perfect glass fiber, the advanced coherent transmission, the automated optical switching, and now this intelligent software layer, they're all working together for one single, really ambitious goal: to build the fundamental infrastructure for a fully connected and intelligent digital world that's available for every single person, home, and organization.
When you think about it, from the simple physics of light traveling through glass all the way to AI-powered network management, the evolution of optical transmission is it's remarkable. And it leaves us with one final, kind of mind-bending thought. We have basically mastered sending information at the physical speed limit of our universe. So what new possibilities does that unlock next? Thanks for tuning in.